The German colonel's hands trembled as he lowered his binoculars. Not from fear, he had seen enough of war by 1945 to know what fear felt like, but from something far more unsettling. Disbelief, the kind that gnaws at the foundation of everything you thought you understood about the world. It was March 22nd, 1945, just past midnight on the western bank of the Rhine River near the town of Oppenheim. The Colonel Oberstleutnant Klaus Fischer, a veteran engineer officer who had built fortifications across occupied France and defensive positions along the Siegfried Line, stood among the ruins of a blown bridge, watching the opposite shore through the darkness. Behind him, what remained of his battalion waited in concealed positions, ready to repel any American attempt to cross. He checked his watch again. 11:47 in the evening. The Americans had begun their bridging operation at approximately 10 o'clock. 1 hour and 47 minutes ago. He had been watching since the first pontoon touched the water. According to every manual, Fischer had studied at the Wehrmacht Engineering Academy in Berlin. According to every doctrine drilled into him during his 15 years of military service, what he was witnessing could not be happening. The construction of a tactical bridge across a river of this magnitude over 400 feet of fast-moving water, capable of bearing the weight of armoured vehicles under combat conditions, required a minimum of 2 weeks. 2 weeks of surveying, positioning, anchoring, and assembly. 2 weeks of vulnerable, exposed construction work gave defenders ample time to concentrate artillery fire, to position anti-tank weapons, and to prepare counterattacks. The Americans had been at it for less than 2 hours, and they were almost finished. Fischer raised his binoculars again, adjusting the focus in the dim moonlight. He could see them clearly now, dozens of American engineers, working in coordinated teams, moving with a precision that seemed almost mechanical. Pontoons were being floated into position with remarkable speed. Steel treadway sections were being rolled out and connected, while men stood waist-deep in the frigid March water. Small boats with outboard motors pushed the floating sections against the current with practiced efficiency. There was no hesitation in their movements, no confusion, no wasted motion. They worked as if they had done this 1,000 times before. Perhaps they had. "Herr Oberstleutnant," a voice said behind him. Fischer turned to see his adjutant, a young lieutenant named Werner Hoffmann, holding a field telephone. "Artillery Command is requesting target coordinates. They want to know if we should begin the barrage." Fischer looked back at the river. The bridge was now more than 2/3 complete. American tanks were already moving into position on the western bank, engines idling, waiting for the signal to cross. In darkness, he could see the shapes of countless more vehicles, half-tracks, trucks, self-propelled guns lined up in columns that seemed to stretch back for miles. "Herr Oberstleutnant?" Hoffmann prompted. Fischer lowered his binoculars slowly. Artillery fire now would be largely useless. Even if they scored direct hits, even if they destroyed sections of the bridge, the Americans would simply repair it or build around it. He had watched them do exactly that an hour ago, when a lucky shell strike had torn a hole in one of the pontoons. Within 15 minutes, they had patched the damage, and the section was back in place. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. "Tell the artillery command to hold fire," Fischer said quietly. "Conserve ammunition. We will need it when they cross." But even as he spoke the words, Fischer felt something crack inside him, not his courage, not his will to fight, but something deeper, his certainty, his understanding of how war worked, of what was possible and what was not. The Americans would cross the Rhine tonight, not in 2 weeks, not even in 2 days. Tonight, and there was nothing his training, his experience, or his understanding of military engineering could do to stop it. This was not the war he had learned to fight. To understand the magnitude of what Fischer witnessed that night, to grasp why it shattered not just German defensive plans but the psychological foundations of Wehrmacht confidence, We must first understand what the Rhine River meant to Germany in March of 1945. The Rhine was not merely a river. It was a symbol, a barrier, a promise. For over 2,000 years, it had served as one of Europe's most significant natural defensive lines. The Roman Empire had struggled to maintain control beyond it. Charlemagne had used it to define the boundaries of his realm. Napoleon had recognized its strategic importance. Every German schoolchild learned about Vater Rhine, Father Rhine, the great river that divided and protected their homeland. By March of 1945, it represented something even more crucial: time. The German military was in desperate straits. The Battle of the Bulge, Hitler's last major offensive in the West, had failed catastrophically in January. The Wehrmacht had been pushed back across France and Belgium. The Allies were approaching the German frontier from all directions. In the east, Soviet armies were already deep into German territory. In the west, American and British forces had liberated France and were pressing against Germany's western border. But the Rhine offered hope, because rivers, particularly rivers of this magnitude, were force multipliers for defenders. They channeled attacking armies into predictable crossing points. They slowed offensives to a crawl. Most importantly, they bought time. Time to regroup. Time to reorganize. Time to bring up reinforcements. Time to prepare the defense of the fatherland itself. German military doctrine regarding river crossings was based on centuries of European warfare and refined through 2 world wars. The Wehrmacht's engineering manual, the Pioneer Dienstvorschrift, specified in precise detail the requirements for constructing tactical bridges under combat conditions. For a river the width and depth of the Rhine, with its powerful current and fluctuating water levels, the manual stipulated a construction timeline of 14 to 21 days for a bridge capable of bearing heavy loads. This was not guesswork. It was based on German engineering experiences in Russia, in France, in Poland. It accounted for the time needed to assemble materials, survey the riverbed, anchor pontoons against the current, and construct the load-bearing superstructure. It factored in the complications of working under fire, of equipment failures, of weather delays. 14 to 21 days. That was the bedrock assumption upon which German defensive planning rested in March of 1945. General der Panzertruppen Friedrich von Mellenthin, one of the Wehrmacht's most experienced operational commanders, had spent the winter of 1944 organizing defensive positions along Germany's western approaches. His memoirs, Panzer Battles, written after the war, provide crucial insight into German thinking during this period. Von Mellenthin wrote extensively about the strategic calculations that informed Wehrmacht defensive doctrine in the war's final months. The German High Command understood that they could not stop the Allied advance indefinitely. The material superiority of the Americans and British was overwhelming. The numerical advantage was insurmountable. But what they could do, what they had to do was slow the Allied advance enough to achieve one of 2 outcomes. Either force a negotiated peace that would prevent the complete occupation of Germany, or buy enough time for the development of new wonder weapons that might shift the strategic balance. The Rhine was central to this strategy. Every day the Allies spent building bridges was a day the Wehrmacht could use to prepare defensive positions in depth behind the river. Every week spent on river crossings was a week that German industry relocated underground to avoid Allied bombing could produce more jet fighters, more rockets, more of the advanced weaponry that Nazi propaganda promised would turn the tide of war. Von Mellenthin, who served on both the eastern and western fronts and witnessed Soviet and American operational methods firsthand, noted a crucial distinction in his post-war writings. The Soviets, he observed, approached river crossings with overwhelming force and shocking disregard for casualties. They would throw bridges across under fire, accepting massive losses in exchange for rapid penetration. The cost in lives was staggering, but the method was effective through sheer brutal application of mass. The Americans, von Mellenthin had observed throughout the French campaign, operated differently. They relied on firepower, on air superiority, on methodical preparation. They were cautious, they prepared thoroughly. They minimized casualties through superior logistics and overwhelming material advantage. This approach, while effective, was also time-consuming, or so the Germans believed. What von Mellenthin and his fellow officers failed to understand in March of 1945 was that the Americans had not just brought superior industrial capacity to the European theatre, they had brought something more profound. They had industrialized warfare itself. They had taken the chaos and unpredictability of combat engineering and transformed it into something resembling a factory production line. The U.S. Army Corps of Engineers in 1945 represented the culmination of a dramatic transformation in American military doctrine that had begun in the years before the war. The United States entered World War II with many disadvantages relative to the European powers. American soldiers had no recent combat experience. American officers had not fought a major war since 1918. American equipment, while improving, lagged behind German technological sophistication in many areas. But the United States possessed two enormous advantages: vast industrial capacity and an institutional culture that prized systematic efficiency over individual brilliance. The American military establishment, shaped by officers who had come of age during the Industrial Revolution, who had seen the transformation of American manufacturing through assembly line production and scientific management, approached warfare with the mindset of engineers rather than warriors. They believed that military operations, like factory production, could be broken down into component tasks, standardized, practiced, and optimized. This was particularly true of the Corps of Engineers. Unlike infantry or armor, where individual courage and tactical flexibility were paramount, engineering was fundamentally about systems, about processes, about repeatable procedures that could be executed reliably under pressure. The pontoon bridge technology the Americans brought to the Rhine in March of 1945 was called the M2 treadway bridge system. It had been developed in the late 1930s and refined through extensive testing and field experience. The system consisted of pneumatic rubber pontoons, each 33 feet long, and capable of supporting tremendous weight when properly inflated, connected by steel treadway sections that formed the bridge deck. The genius of the M2 system was not in its individual components, which were relatively simple, but in its modularity. Each pontoon was identical, each treadway section was identical. The connections were standardized. This meant that assembly could be broken down into repetitive tasks that could be practiced until they became automatic. And practiced. The engineer combat battalions that reached the Rhine in March of 1945 had been building bridges since Normandy. They had bridged rivers across France. They had rebuilt bridges destroyed by retreating Germans. They had constructed tactical bridges under fire, under time pressure, under every conceivable field condition. By the time they reached the Rhine, they had refined their procedures to the point where bridge construction had become almost routine. The 291st Engineer Combat Battalion, one of the units that would participate in the Rhine crossings, had kept detailed records of their bridge construction operations throughout the European campaign. These records, preserved in the National Archives, reveal a unit that approached engineering with obsessive attention to efficiency. After each bridge construction, the battalion would conduct what they called after-action reviews, detailed analyses of what had worked, what had failed, and how procedures could be improved. They timed every step of the process. They identified bottlenecks. They experimented with different team configurations. They practiced equipment handling until each soldier could perform their role without conscious thought. They developed hand signals for coordination in situations where verbal communication was impossible. They created redundant systems so that if one team was hit by enemy fire, another could seamlessly take over. By March of 1945, the men of the 291st could assemble a pontoon bridge in their sleep, and they were about to prove it. Lieutenant Colonel Harvey Fraser, commanding officer of the 291st Engineer Combat Battalion, received his orders on the evening of March 22, 1945. General George S. Patton's Third Army had established a small infantry bridgehead on the eastern bank of the Rhine near Oppenheim through a nighttime crossing in assault boats. Now Patton wanted armour across, immediately. Fraser was a West Point graduate, class of 1932, who had spent the Depression years overseeing civilian conservation corps projects before returning to active duty in 1940. He was not a combat arms officer in the traditional sense. He had never commanded tanks or led infantry assaults, but he understood systems, he understood logistics, and he understood how to build bridges quickly. Fraser's orders were straightforward. Construct a treadway pontoon bridge across the Rhine at Oppenheim. Minimum load capacity, 30 tons, sufficient to bear an M4 Sherman tank. Timeline, as fast as possible. Fraser assigned specific responsibilities to each company. First company would handle pontoon launching and positioning. The second company would manage treadway placement and connection. Third company would provide security and manage traffic flow once the bridge was complete. The battalion's boat teams would use small craft with outboard motors to maneuver the pontoons against the current. There was no dramatic speech, no appeals to heroism. Fraser simply told his officers what needed to be done, confirmed that they had the necessary equipment and materials, and sent them to brief their men. At 10:17 in the evening, the first trucks began unloading pontoons at the western bank of the Rhine near Oppenheim. What happened over the next 2 hours would fundamentally challenge German assumptions about what was militarily possible. The Rhine at Oppenheim was 420 feet wide. The current ran at approximately 3 miles per hour, not tremendously fast, but strong enough to make pontoon positioning difficult. The water was cold, near freezing, and deep enough that anchoring would require substantial cable work. The first pontoon hit the water at 10:23 in the evening. 4 engineers wrestled the massive rubber bladder, inflated with compressed air from portable pumps down to the water's edge, and pushed it into the current. A boat team immediately motored out, secured a tow line, and began guiding the pontoon into position at the western bank. By 10:30, 3 pontoons were in the water. By 10:45, the first treadway section was being rolled into place. The process was organized chaos, dozens of men moving in coordinated teams, each focused on their specific task, each trusting that the others would do their jobs. There was remarkably little verbal communication. Hand signals sufficed. The men had done this so many times that they anticipated each other's movements. Private First Class James Donovan, a member of First Company's pontoon team, later described the experience in an interview conducted by military historians in 1987. Donovan, who was 19 years old in March of 1945, had joined the 291st after being wounded in the Battle of the Bulge and reassigned from an infantry unit. "It wasn't like combat," Donovan recalled. "In combat, everything's confused. You don't know what's happening half the time. But the bridge work, we'd done it so much that your body just knew what to do. You'd grab the pontoon at a certain spot. You'd push it at a certain angle. You'd wait for the boat team to take the line. Then you'd move to the next one." I didn't think about it. None of us did. We just moved. The German artillery began firing at approximately 11 o'clock in the evening. The shells fell haphazardly. German ammunition stocks were severely depleted by this stage of the war, and fire discipline was poor. Most of the rounds fell into the river or exploded harmlessly on the western bank. But at 11:17, a shell scored a direct hit on a pontoon that was being manoeuvred into position. The explosion tore a 6-foot gash in the rubber bladder. Air hissed out. The pontoon began to sink. Without pausing, the boat team cut the damaged pontoon loose and let it drift downstream. A replacement pontoon was already being pushed into the water. The damaged pontoon was hauled to shore by a salvage team, who immediately began patching the tear with vulcanizing rubber and a portable heat source. Within 15 minutes, the pontoon was reinflated and back in service. The bridge construction never stopped. By midnight, more than half the bridge was complete. The pontoons floated in a line across the dark water, steel treadway sections gleaming faintly in the moonlight. Engineers worked in the water itself, some standing chest-deep in the frigid Rhine, securing anchor cables to the riverbed to prevent the current from twisting the partially completed structure. Corporal Michael Petrosky, a member of 2nd Company, was one of the men in the water that night. In the letter to his family written 3 weeks later, Petrosky described the experience. "You stop feeling your legs after about 10 minutes. The water's so cold it doesn't feel like water anymore, just like something heavy pressing on you. But you keep working because you know the guys on the bank are counting on you, and the guys on the other side are counting on you, and if you stop, everything stops." On the eastern bank, Oberstleutnant Fischer continued to watch. His initial disbelief had given way to something darker, a cold, creeping realization that everything he had been taught about American military capabilities was fundamentally wrong. The Americans were not cautious. They were not slow. They were not methodical in the sense that German doctrine understood methodical. They were something else entirely. They were a machine, a human machine perhaps, but a machine nonetheless. Each soldier a cog, each team a component, the entire battalion functioning as a single coordinated mechanism designed to turn raw materials into finished bridges at a rate that defied everything Fischer understood about engineering. He thought about the bridges his own engineers had built across Russia during Operation Barbarossa, the days of surveying, the careful calculations, the attention to detail, the pride they had taken in constructing precisely engineered structures that would stand for years if needed. The Americans were building what amounted to a disposable bridge, simple, crude even, but functional and fast. They did not care about elegance, they cared about speed, and they had apparently practiced speed so relentlessly that they could achieve in hours what German doctrine said required weeks. Fischer turned to his adjutant. "How many of these bridges have they built?" he asked quietly. Hoffman consulted a sheaf of intelligence reports. American engineers have constructed tactical bridges at over 40 locations across France and the Low Countries since D-Day. Herr Oberstleutnant. Some were permanent structures. Many were temporary crossings like this one. 40, Fischer repeated. 40 bridges. 40 opportunities to practice. 40 iterations to refine their procedures. 40 lessons learned and incorporated into their doctrine. The Wehrmacht had spent 4 years building an empire across Europe. The Americans had spent those same 4 years building a system. And now, at the Rhine, those two approaches were colliding. At 1:53 in the morning on March 23, 1945, 1 hour and 53 minutes after the first pontoon touched the water, Lieutenant Colonel Harvey Fraser walked across the completed bridge. 420 feet of steel and rubber stretching across the Rhine River, load-tested and certified ready for armoured vehicles. Fraser reached the eastern bank, turned, and signalled to the western shore. The first M4 Sherman tank began its crossing. The bridge held. The sound of the Sherman tank's engine echoed across the water as 33 tons of American armour rolled onto the pontoon bridge. The steel treadway sections groaned under the weight. The pontoons dipped visibly into the dark water, their rubber bladders compressing under the massive load. For a moment, the entire structure seemed to shudder. Then it stabilized. The tank continued forward, tracks clanking against steel, moving at a steady 5 miles per hour. Behind it, the driver of a second Sherman waited for the signal to proceed. Behind that tank, dozens more. Behind the tanks, half-tracks filled with infantry. Behind the half-tracks, supply trucks. Behind the trucks, self-propelled artillery. An entire armoured column waiting to cross a bridge that, according to German military doctrine, should not have existed for another 12 days. Oberstleutnant Fischer watched the first tank reach the eastern bank at 1:58 in the morning. He watched the second tank begin its crossing at 2:03. watched the third at 2:07. By 2:30 in the morning, a steady stream of American armor was flowing across the Rhine. The impossible bridge had become a highway. Fischer had fought across Russia. He had witnessed the savagery of the Eastern Front. He had seen Soviet human wave attacks that accepted horrific casualties in exchange for territorial gains. He had endured the siege of Sevastopol, where both sides had fought with desperate ferocity for every inch of ground. He had seen what industrial warfare looked like when two massive armies collided with total disregard for human cost. But this was different. This was not about courage or sacrifice or determination. This was about systems, about processes, about the relentless application of organized efficiency. The Americans had not overwhelmed German defenses with superior numbers or firepower. They had simply rendered those defenses irrelevant by operating on a timeline that made defensive preparation impossible. As dawn broke on March 23rd, Fischer could see the full extent of the American operation. The pontoon bridge stretched across the Rhine, a ribbon of steel and rubber that should not have existed. On the western bank, seemingly endless columns of vehicles waited to cross. In the air above, American fighter bombers circled lazily, unchallenged by a Luftwaffe that barely existed anymore. And on the eastern bank, American infantry were already digging in, establishing a bridgehead perimeter that was expanding by the hour. Fischer's battalion received orders to withdraw at 0600 hours. There was no point in defending a position that had already been outflanked. No point in wasting men and ammunition on a battle that was already lost. The Americans were across the Rhine. They would be across it at a dozen other points within days. The defensive line that was supposed to buy Germany weeks or months had lasted less than a day. As Fischer supervised the withdrawal of his unit, he found himself thinking not about tactical considerations or strategic implications, but about a more fundamental question. How had the German military, the Wehrmacht, that had conquered most of Europe in less than 2 years, failed so completely to understand their enemy? The answer, he was beginning to realize, lay not in German weaknesses, but in a fundamental misunderstanding of American strengths. The Wehrmacht had prepared to fight an American army that resembled European forces, an army that relied on traditional military virtues like courage, tactical brilliance, and operational art. What they encountered instead was something that did not fit their conceptual framework, an army that had industrialized warfare itself, that treated military operations as engineering problems to be solved through systematic application of resources and refined procedures. The Germans had built an army of craftsmen. The Americans had built an army of factory workers. And in 1945, the factory workers were winning. The Rhine crossing at Oppenheim was not an isolated incident. It was a pattern repeated at Remagen, at Wesel, at Boppard, at dozens of crossing points along the river's length in March of 1945. At each location, American engineers performed variations of the same engineering miracle that had shocked Fischer at Oppenheim. At Remagen, the story was slightly different but equally revealing. On March 7, 1945, American forces of the 9th Armored Division had captured the Ludendorff Bridge intact, one of the few Rhine bridges the Germans had failed to demolish before Allied troops arrived. For 10 days, this single bridge served as the primary crossing point for American forces, funneling thousands of troops and vehicles onto the eastern bank. But the Ludendorff Bridge was not designed to handle such traffic. It had been damaged during the German demolition attempt. It was under constant artillery, bombardment from German forces attempting to destroy what they had failed to demolish during their retreat. And on March 17th, the bridge collapsed, killing 28 American engineers who were working on emergency repairs. The loss of the Ludendorff Bridge should have been a major setback for American operations. It was the only intact bridge across the Rhine. Its collapse left thousands of American troops on the eastern bank with no direct supply line. The American response: build a new bridge. The 291st Engineer Combat Battalion, along with several other engineer units, was rushed to Remagen. Construction began on March 18th. 32 hours later, on March 19th, a new tactical bridge was operational, capable of handling the same traffic as the collapsed Ludendorff Bridge. 32 hours, not 2 weeks, not even 2 days. German commanders monitoring American operations at Remagen initially believed the intelligence reports were errors. When aerial reconnaissance confirmed that the Americans had indeed constructed a new bridge in just over a day, the psychological impact rippled through Wehrmacht headquarters. If the Americans could replace a major bridge in 32 hours, what was the point of demolishing bridges at all? Every blown bridge, every destroyed crossing point, was at best a temporary inconvenience to an enemy who could simply build around the obstacle faster than defenders could reorganize their positions. General der Panzertruppen von Mellenthin, who was attempting to coordinate German defensive operations in the Rhine sector during this period, later wrote extensively about the psychological impact of American engineering capabilities. In his memoir, Panzer Battles, published in 1956, von Mellenthin devoted an entire chapter to what he called the American system. We had understood American material superiority in quantitative terms, von Mellenthin wrote. We knew they had more tanks than we did, more planes, more trucks, more of everything. What we had failed to understand was that they had applied their industrial methods not merely to the production of weapons, but to the conduct of war itself. They had turned warfare into a form of mass production. Von Mellenthin described attending a meeting of senior Wehrmacht officers in late March of 1945, shortly after the Rhine crossings. The purpose of the meeting was to assess defensive options for the interior of Germany. One officer proposed using Germany's extensive river system, the Weser, the Elbe, the various tributaries as successive defensive lines, each one buying time for the organization of the next. Von Mellenthin recalled his response. I told them it was pointless. The Americans would bridge each river in a matter of hours. We could not build defensive positions faster than they could build bridges. We were not fighting a conventional army. We were fighting an engineering corporation with unlimited resources. The comment, von Mellenthin wrote, was met with stunned silence. Then anger. Then, gradually, reluctant acceptance, because everyone in that room had seen the intelligence reports. Everyone knew what the Americans were achieving at the Rhine, and no amount of traditional military thinking could explain it away. To fully understand the magnitude of what American engineers accomplished at the Rhine, we must examine the specific procedures and technologies that made such rapid bridge construction possible. This requires delving into details that might seem mundane, the specifications of equipment, the organization of labor, the logistics of material supply. But these details reveal the systematic thinking that defined American military operations in the war's final year. The M2 treadway bridge system that the Americans used at the Rhine consisted of several key components, each designed with modularity and speed of assembly in mind. The basic unit was the pneumatic pontoon, a rubber bladder 33 feet long, 5 feet wide, and 3 feet deep when inflated. Each pontoon weighed approximately 600 pounds when deflated and could be transported in the back of a standard 2.5-ton truck. When inflated with compressed air, each pontoon could support over 10 tons of weight. The treadway sections, the actual roadway of the bridge, were made of steel grating and aluminum framing. Each section was 25 feet long and 12 feet wide, weighing approximately 1,200 pounds. The sections were designed to interlock with standardized connectors that could be secured with bolts in under 2 minutes. The steel grating allowed water to drain through, preventing the accumulation of weight on the bridge deck during rain. The anchor system consisted of steel cables and ground anchors driven into the riverbed or riverbank. Each cable was designed to withstand tensions of up to 15 tons, providing stability against current and wind loads. The cables were attached to the pontoons at standardized connection points, spaced every 8 feet along the pontoon's length. What made the M2 system revolutionary was not any individual component. Pneumatic pontoons had existed for decades. Steel treadways were not new technology, but rather the standardization of every element and the resulting speed of assembly. Because each pontoon was identical, soldiers did not need to make decisions about which pontoon to use where. Because each treadway section was identical, there was no need to customize connections. Because every component was designed to be handled by a team of 4 men, no special equipment was required beyond standard trucks and small boats. The American military had tested and refined the M2 system extensively before the Rhine crossings. The engineer school at Fort Belvoir, Virginia, had conducted time trials throughout 1943 and 1944, identifying bottlenecks and developing procedures to eliminate wasted motion. They discovered, for instance, that having separate teams for pontoon launching and treadway placement was more efficient than having single teams do both tasks. They found that using boat crews to position pontoons was faster than trying to guide them into place from shore. They determined the optimal team size for each task, the most efficient sequence of operations, and the best methods for quality control under combat conditions. By the time American engineer units reached Europe, they were working from a playbook that had been refined through hundreds of training exercises. The procedures were documented in field manuals that specified not just what to do, but exactly how to do it, with illustrations showing proper hand positions, optimal body mechanics, step-by-step sequences that minimized effort and maximized speed. This level of procedural documentation was characteristic of American military training in World War II, the US. The Army produced field manuals for everything, not just major operations like bridge building, but minute details like the proper way to dig a foxhole, the optimal method for cleaning a rifle, and the most efficient technique for loading ammunition. This might seem like excessive bureaucracy, but it reflected a fundamentally different philosophy of warfare than European armies embraced. European military tradition, particularly German tradition, emphasized the concept of Auftragstaktik, mission-type tactics. Officers were given objectives and expected to use their initiative, creativity, and tactical judgment to achieve those objectives. This system worked brilliantly when commanders were skilled and experienced. It produced remarkable operational flexibility and allowed German forces to adapt quickly to changing battlefield conditions. But it also meant that performance varied dramatically based on the quality of leadership. A brilliant commander could achieve remarkable results. A mediocre commander could fail catastrophically. And as the war progressed and Germany lost more and more of its experienced officers, the quality of leadership declined precipitously. The American system was different. It assumed that individual soldiers and junior officers might not be tactical geniuses. It assumed that in the chaos of combat, people would be tired, scared, and unable to think clearly. So it tried to eliminate the need for creative thinking by reducing complex operations to simple, repeatable procedures that could be executed even under extreme stress. This approach had drawbacks. It could lead to inflexibility when situations deviate from standard procedures. It sometimes produced soldiers who followed instructions mechanically, without understanding the broader purpose of their actions. But it also produced a military that could sustain operations with a constant turnover of personnel, that could train replacements quickly, and that could maintain consistent performance levels, regardless of individual leadership quality. At the Rhine in March of 1945, the American system proved devastatingly effective. The Rhine crossings produced cascading effects throughout the Wehrmacht's command structure that extended far beyond the immediate tactical situation. As word spread of American engineering capabilities, German defensive planning underwent a fundamental crisis of assumptions. One of the most revealing documents from this period is an intelligence assessment produced by the Wehrmacht Operations Staff on March 25, 1945, 2 days after the Oppenheim crossing. The document, captured by Allied forces after the war and now preserved in the National Archives, provides a window into German military thinking as it grappled with the implications of American engineering speed. The assessment begins with a straightforward recitation of facts. American forces had established crossings at Senkelsee Geelofert, multiple points along the Rhine. Tactical bridges had been constructed in time frames ranging from 2 to 32 hours. Traffic density across these bridges exceeded German projections by factors of 3 to 5. But the second section of the assessment reveals something more disturbing, an attempt to explain these facts within the framework of existing German military doctrine. The author of the assessment suggested several possible explanations. Perhaps American intelligence had obtained German bridge construction manuals and specifically designed their procedures to exploit weaknesses in German defensive assumptions. Perhaps the Americans were taking unacceptable casualties in their rush to complete bridges, but were suppressing reports of these losses for propaganda purposes. Perhaps the bridges were shoddily constructed and would fail under sustained use, causing logistical bottlenecks that would slow the American advance. Each of these explanations was wrong. The American had not obtained German manuals. They had developed their own procedures independently. They were not suffering high casualties. The engineer units at the Rhine sustained relatively light losses compared to infantry formations. And the bridges did not fail. They remained operational throughout the final weeks of the war, handling traffic loads that exceeded their design specifications. But the fact that senior Wehrmacht staff officers felt compelled to generate these alternative explanations reveals the depth of the conceptual crisis. They were looking for reasons why American performance was an anomaly, an exception, a temporary phenomenon. They were seeking explanations that would allow them to maintain their existing understanding of how warfare worked. The reality that the Americans had fundamentally reimagined military engineering through systematic innovation and training was too psychologically devastating to accept. It implied that German military excellence, the Prussian tradition of military professionalism, the careful cultivation of tactical brilliance, was simply inadequate against an enemy that had industrialized warfare itself. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The psychological impact of the Rhine crossings was most acute among German engineer officers, men like Oberstleutnant Fischer, who had spent their careers mastering the technical and operational aspects of military engineering. These officers had defined their professional identity around a specific body of knowledge and a particular approach to problem solving. The American bridges did not just defeat them tactically, they invalidated their expertise. Fischer's own fate after the Oppenheim crossing illustrates this psychological dimension. His battalion withdrew eastward, conducting a fighting retreat through southern Germany. On April 2, 1945, Fischer's unit was surrounded by American forces near the town of Würzburg. After a brief firefight in which several of his men were killed, Fischer ordered his battalion to surrender. In the prisoner of war interrogation that followed, Fischer was questioned by American intelligence officers about German defensive preparations and engineering capabilities. The interrogation transcript, declassified in 1983, reveals a man struggling to reconcile his professional training with the evidence of American capabilities. When asked about German assessments of American bridge-building capacity, Fischer initially responded according to German doctrine. Our manuals specified that tactical bridge construction across a river the size of the Rhine would require 14 to 21 days under combat conditions. This assessment was based on extensive German engineering experience across multiple theatres of war. The interrogator then showed Fischer photographs of the Oppenheim Bridge, along with time-stamped documentation of the construction timeline. Fischer examined the photographs in silence for several minutes. When he finally spoke, his words were carefully measured. These photographs show a completed bridge. The timestamps, if accurate, indicate construction in under 2 hours. This is not possible according to any engineering principles I am aware of. The interrogator pressed, "But the bridge exists. You saw it yourself. How do you explain this?" Fischer's response is recorded in the transcript. "I cannot explain it. I can only observe that your engineering methods are fundamentally different from ours. We approach bridge construction as a problem of careful planning and precise execution. You appear to approach it as a problem of rapid assembly using standardized components. Your method prioritizes speed over permanence. It works, clearly, but it violates everything I was taught about proper engineering. The interrogator then asked whether Fischer believed other German officers shared his assessment of American capabilities. Fischer's answer revealed the broader psychological crisis. Many officers still believe that American success is due primarily to material superiority, that you simply have more resources than we do. This is true, but it misses the larger point. Your advantage is not merely quantitative, it is methodological. You have created a military system that operates according to principles that are foreign to European military tradition. Fischer paused, then added, I do not know if my fellow officers will accept this conclusion. It is easier to believe that we lost because you had more tanks, more planes, more supplies. It is more difficult to accept that we lost because you organized warfare more effectively than we did. The Rhine crossings of March 1945 became a case study in American military efficiency that would influence engineering doctrine for decades after the war. The U.S. Army Engineer School incorporated lessons from the Rhine operations into its training curriculum. The procedures developed by units like the 291st Engineer Combat Battalion became the basis for standardized bridge construction protocols. The M2 treadway bridge system, with minor modifications, remained in service with the U.S. military into the 1980s. But the significance of the Rhine bridges extended beyond engineering. They represented a philosophical approach to warfare that would define American military operations throughout the Cold War and beyond. The belief that complex problems could be solved through systematic analysis, standardized procedures, and intensive training that made difficult tasks routine. This approach had its critics, both at the time and in subsequent decades. Some argued that it produced soldiers who were technicians rather than warriors, who could follow procedures but lacked tactical creativity. Others suggested that the emphasis on standardization stifled innovation and made American forces predictable. German military theorists, particularly those writing in the immediate post-war period, often portrayed American military success as the triumph of material quantity over tactical quality. But these criticisms missed the fundamental insight that the Rhine crossings revealed. In modern warfare, the ability to execute routine tasks with extreme efficiency is often more valuable than tactical brilliance. An army that can build bridges in 2 hours does not need to find the perfect crossing point. Every crossing point becomes viable. An army that can supply its forces reliably does not need brilliant maneuver warfare. It can simply advance steadily, knowing that logistics will not fail. The Wehrmacht had built an army designed for short, decisive campaigns where tactical brilliance could achieve strategic victory. Army built a military machine designed for sustained operations, where systematic efficiency would eventually overwhelm any opponent. At the Rhine, these two philosophies collided, and the outcome was never in doubt. The aftermath of the Rhine crossings transformed not just the military situation in Germany, but the psychological landscape of the Wehrmacht's remaining leadership. As American forces poured across the river at multiple crossing points throughout late March and early April of 1945, German commanders faced a stark reality. There would be no last stand at the Rhine. There would be no time bought for negotiation or wonder weapons. The war was lost, not just militarily but conceptually. The speed of the American advance after crossing the Rhine exceeded even optimistic Allied projections. Army Group B, the German formation responsible for defending the Ruhr industrial region, was encircled by April 1st. Within 2 weeks, over 300,000 German soldiers surrendered in what became the largest mass capitulation of German forces on the Western Front. The infrastructure that was supposed to give Germany months of defensive capability collapsed in weeks. General der Panzertruppen von Mellenthin, who survived the war and wrote extensively about his experiences, devoted considerable attention in his post-war writings to what he called the engineering gap, the disparity between German and American capabilities in military logistics and construction. Von Mellenthin argued that this gap was more decisive than the better-known gaps in air power or armoured warfare. We knew the Americans had air superiority, von Mellenthin wrote in 1956. We knew they had more tanks. We had learned to fight under these disadvantages, to move at night, to use terrain, to employ tactical sophistication to offset material inferiority. But the engineering gap was different. It meant that even when we executed textbook defensive operations, the Americans could simply bypass or overcome our positions faster than we could, reposition our forces. They made defensive warfare obsolete by operating on a timeline we could not match. This recognition that the Americans had fundamentally altered the tempo of warfare through engineering efficiency appeared repeatedly in German military memoirs and analyses produced after the war. It represented a grudging acknowledgement that the Wehrmacht's defeat was not merely a matter of being outnumbered or outgunned, but of being systematically outmaneuvered by an enemy that had reimagined how war could be fought. The fate of individual engineer officers like Oberstleutnant Fischer illustrates the personal dimensions of this conceptual collapse. Fischer spent the remainder of the war in American captivity, first at a temporary prisoner of war facility in Bavaria, then at a larger camp near Reims, France. The interrogation transcripts from his time in captivity reveal a man attempting to intellectually process experiences that challenged everything he had been taught about his profession. In a follow-up interrogation conducted on April 15, 1945, Fischer was asked to assess German engineering doctrine in light of the Rhine crossings. His response was notably more analytical than his earlier, more defensive comments. German engineering doctrine was developed for a different kind of war. We assumed that crossing major rivers would be decisive, strategic moments that defenders would have time to prepare, that attackers would need weeks to build the infrastructure for crossing. These assumptions were valid in the First World War. They remained valid during our campaigns in Poland and France, but the Americans have changed the fundamental parameters. They have collapsed the timeline to the point where river crossings are tactical actions, not strategic operations. Fischer continued, "What I find most troubling is not that we lost these engagements. That was inevitable given the material situation by 1945. What troubles me is that we never understood what we were facing. We kept preparing for a war that followed. Familiar patterns build defenses, force the enemy to come to us, make them pay for every meter. But the Americans were not fighting that war. They were fighting a war where speed and systematic efficiency made traditional defensive advantages irrelevant." When asked what lessons German engineers might learn from American methods, Fischer's answer revealed both intellectual honesty and professional pride. The American approach is effective, but it requires resources and organizational culture that Germany does not possess. We cannot simply copy their methods. But we must understand that military engineering is not merely about technical knowledge. It is about systems, about creating procedures that can be executed reliably under pressure by ordinary soldiers, not just by skilled specialists. Fischer was released from American custody in June of 1946. He returned to his hometown of Dresden, which had been devastated by Allied bombing and was now under Soviet occupation. He worked as a civil engineer during the Reconstruction period, specializing in bridge repair and river management. He never spoke publicly about his wartime experiences until the early 1970s, when he was interviewed by a doctoral student researching German engineering operations in World War II. In that interview, conducted in 1972 when Fischer was 74 years old, he reflected on the Rhine crossings with the perspective of nearly 3 decades. "I spent my career believing that engineering was about precision, exact calculations, careful planning, perfect execution. The Americans taught me that engineering could also be about speed, about good enough solutions implemented quickly. Both approaches have merit. In peacetime, I still prefer precision. But in war, the Americans were right. Speed matters more than perfection." The organizational innovations that enabled American engineering success at the Rhine did not emerge spontaneously in 1945. They were the product of institutional learning that began long before the United States entered World War II and continued throughout the conflict. Understanding this development reveals how military organizations can systematically cultivate capabilities that provide decisive advantages. Army Corps of Engineers had a long history dating back to the early Republic, but the organization that reached the Rhine in 1945 bore little resemblance to its pre-war predecessor. The transformation began in earnest in 1940, when American military planners, observing the German campaigns in Poland and France, recognized that modern warfare would require unprecedented engineering support. The key insight was that engineering could not be treated as a specialized function performed by small elite units. Modern mechanized warfare, with its heavy reliance on mobility and logistics, required engineering capabilities to be distributed throughout the army. Every division needed engineer support. Every corps needed bridge-building capacity. Every army needed the ability to rapidly construct or repair infrastructure. This meant training thousands of engineers in a short period, not just teaching them engineering principles, but drilling them in standardized procedures until those procedures became automatic. The engineer school at Fort Belvoir expanded dramatically, developing training programs that could transform civilians into military engineers in 12 to 16 weeks. The curriculum emphasized practical skills over theoretical knowledge, repetitive training over creative problem-solving. Critics at the time, both within the military and in the civilian engineering community, argued that this approach would produce mediocre engineers who could follow instructions but lacked true technical competence. The criticism had merit. Many wartime engineers had only superficial understanding of the physics and mathematics underlying their work. But the military did not need engineers who could design bridges from first principles. It needed engineers who could assemble standardized bridge components quickly and reliably under combat conditions. The training regime developed at Fort Belvoir became the model for American military technical training throughout the war. Students learned by doing. They built practice bridges, tore them down, built them again. They timed themselves. They competed in teams. They practiced under simulated combat conditions with explosions and smoke and shouted instructions. They worked at night. They worked in the rain. They worked until the procedures became muscle memory. This training philosophy, emphasizing repetition and standardization over technical depth, produced engineer units that might not have been able to calculate load-bearing tolerances from first principles, but could execute complex operations with remarkable consistency. It was the military equivalent of assembly line manufacturing. Break complex tasks into simple steps, train workers to perform those steps efficiently, then coordinate the steps into a smooth production process. The 291st Engineer Combat Battalion that built the bridge at Oppenheim in under 2 hours had built over 30 bridges across Europe before reaching the Rhine. Each bridge construction was both an operational mission and a training exercise. After-action reviews identified inefficiencies. Procedures were refined. Equipment was modified based on field experience. By March of 1945, the battalion was operating at peak efficiency, a well-oiled machine in the most literal sense. The contrast between American and German engineering doctrine reflected deeper differences in how the two militaries understood expertise and efficiency. German military culture, rooted in Prussian traditions, venerated the concept of the highly trained specialist, the master craftsman who brought years of experience and technical knowledge to complex problems. This cultural orientation produced remarkable individual excellence. German engineers were, on average, better educated and more technically sophisticated than their American counterparts. But individual excellence has limits. A brilliant engineer can design an optimal bridge, but if bridge construction requires 2 weeks, that timeline constrains operational planning regardless of engineering quality. A technically sophisticated approach might produce a more elegant solution, but elegance is less valuable than speed in combat situations, where the enemy is also taking action. The Americans, coming from an industrial culture that had revolutionized manufacturing through mass production techniques, approached military operations with a different mindset. They asked not, "How can we build the best bridge?" but rather, "How can we build adequate customer partners?" bridges as quickly as possible. This subtle shift in framing led to dramatically different solutions. The M2 treadway bridge was not technically sophisticated. It was a simple system of rubber pontoons and steel decking. A German engineer assessing the design in isolation might have found it crude compared to more elegant German designs. But the M2 system had one overwhelming advantage. It could be assembled by average soldiers following standardized procedures in a fraction of the time required by more sophisticated designs. This pattern-trading technical sophistication for operational speed appeared throughout American military operations in World War II. American tanks were generally inferior to German tanks in terms of armor protection and gun power. American fighter planes were not as maneuverable as many of their opponents. American rifles were solid but unremarkable. But American equipment shared a common characteristic. It was designed for mass production, rapid deployment, and maintenance by relatively unskilled personnel. The Germans built Panther tanks with sloped armor and powerful guns that made them superior to American Shermans in most tactical engagements. But Panthers were mechanically complex, required skilled mechanics to maintain, and were produced in relatively small numbers. When a Panther broke down, it often took days to repair. When a Sherman broke down, American maintenance crews could often get it running again in hours, and if repairs were not feasible, a replacement Sherman would arrive quickly. The same logic applied to bridge construction. German bridge designs might have been more sophisticated, but sophistication did not matter if the bridge took 2 weeks to build. The American approach, good enough, fast enough, proved devastatingly effective in the high-tempo operations of 1945. The Rhine crossings had strategic consequences that extended beyond the immediate collapse of German defences. They demonstrated principles of military operations that would influence American defense planning for the remainder of the 20th century and into the 21st. One key lesson was the value of standardization. The M2 treadway bridge system worked so efficiently because every component was interchangeable. This meant that different engineer units could work on the same bridge without coordination problems. It meant that replacement parts were universally compatible. It meant that soldiers transferring between units already knew the procedures. Standardization reduced complexity and enabled the rapid scaling of operations. This principle that standardization enables efficient scaling became foundational to American military logistics. During the Cold War, NATO forces adopted standardized ammunition, standardized communication systems, standardized logistics protocols. This made coalition operations feasible in ways that would have been impossible with incompatible systems. The Rhine bridges of 1945 provided early evidence of standardization's value. Another lesson was the importance of training intensity. The engineer units that performed so effectively at the Rhine had practiced bridge construction dozens of times under realistic conditions. They had refined their procedures through repetition. They had identified and eliminated inefficiencies. This level of training intensity became characteristic of American military preparation in subsequent conflicts. During the Cold War, American armored units would practice their combat drills until they could execute complex maneuvers with minimal verbal communication. Infantry units would rehearse urban combat in elaborate training facilities that simulated enemy cities. Pilot training programs would expose aviators to hundreds of simulated combat scenarios before they ever faced real combat. The underlying philosophy was the same as that which governed engineer training in World War II: intensive, repetitive training that makes complex tasks routine. A third lesson was the value of institutional learning. The American military did not start the war with the procedures that proved so effective at the Rhine. These procedures emerged through systematic analysis of experience. Units kept detailed records of operations. After-action reviews identified what worked and what did not. Lessons learned were incorporated into training and doctrine. This created a feedback loop where operational experience continuously improved organizational performance. The Wehrmacht, despite its tactical sophistication, was less effective at institutional learning. German military culture emphasized the importance of battlefield initiative and tactical flexibility, but it was less systematic about capturing and disseminating lessons learned. German units often repeated mistakes that other units had already identified and solved because there was no effective mechanism for sharing tactical innovations across the army. The American approach, systematic collection of data, analysis of that data, and incorporation of insights into standardized procedures created an organization that became more effective over time, even as individual personnel turned over. This proved crucial in a long war where maintaining experienced units was impossible. The Rhine bridges were built by engineer battalions that had completely replaced their original personnel through casualties and rotation, yet the units performed more efficiently in 1945 than in 1944 because institutional knowledge had been preserved and refined. The human cost of the engineering operations at the Rhine, while relatively light compared to infantry combat, deserves acknowledgement. Engineer units worked under fire, in difficult conditions, performing physically demanding labor that carried significant risk. 28 engineers died when the Ludendorff Bridge at Remagen collapsed on March 17th. Others were killed by artillery fire during bridge construction operations. Many more suffered injuries, broken bones from heavy equipment, frostbite from working in freezing water, shrapnel wounds from German fire. These casualties were accepted as necessary costs of maintaining operational tempo. The American military calculated that rapid bridge construction, even with the attendant risks to engineer personnel, resulted in fewer overall casualties than slower, more cautious approaches that would have prolonged the war. This calculus, accepting tactical risks to achieve strategic speed, characterized American operations throughout the final months of the European War. The families of engineers killed at the Rhine received the same notifications as families of soldiers killed in infantry combat: telegrams expressing the nation's regret, posthumous medals, death benefits, but engineer casualties received less public attention than combat casualties. There were no famous photographs of engineers building bridges under fire equivalent to the images of infantry storming beaches or tanks advancing across fields. Engineering was unglamorous work, and those who performed it were often forgotten in popular accounts of the war. Yet without the engineers, the dramatic advances of American armies in the spring of 1945 would have been impossible. Every tank that crossed the Rhine did so on a bridge that engineers built. Every supply convoy that maintained the pace of advance relied on infrastructure that engineers constructed or repaired. The war correspondents who wrote about American tactical victories rarely mentioned the engineers who made those victories possible, but the engineers were there, working in the background, building the infrastructure of victory. Private First Class James Donovan, the engineer who described working on the Oppenheim Bridge as a process where your body just knew what to do, survived the war and returned to his hometown of Pittsburgh, Pennsylvania. He worked for 40 years as a construction supervisor, specializing in bridge projects. In interviews conducted late in his life, Donovan was asked whether his wartime engineering experience had influenced his civilian career. "It taught me that most things that seem impossible are actually just hard," Donovan replied. "People would tell me a bridge project couldn't be done on schedule, couldn't be done within budget, couldn't be done with the available materials. And I'd think about the Rhine. We built a bridge across the Rhine in less than 2 hours while people were shooting at us. After that, civilian construction problems didn't seem so impossible." The final irony of the Rhine crossings is that they were, in some sense, unnecessary. The Ludendorff Bridge at Remagen had been captured intact on March 7th, providing an immediate crossing point. Additional crossings at Oppenheim and elsewhere, while tactically valuable, were not strictly required to achieve the strategic objective of penetrating into Germany. American forces could have concentrated their advance through the Remagen bridgehead and still achieved rapid victory. But the American High Command chose to construct multiple crossings, partly for operational flexibility, partly to prevent German forces from concentrating against a single bridgehead, but also partly to demonstrate capability. The message the Rhine bridges sent was psychological as much as tactical. American forces could cross rivers wherever and whenever they chose. German defensive planning based on natural obstacles was obsolete. This use of engineering demonstrations as psychological warfare was not unique to the Rhine. Throughout the European campaign, American forces had used their engineering capabilities to demoralize German defenders. When Germans demolished a bridge, Americans would rebuild it within days or build a new one nearby. When Germans flooded areas to create obstacles, Americans would drain the water or build roads through it. The consistent message was that German obstruction tactics, even when executed skillfully, merely delayed American forces briefly. For Wehrmacht commanders, this was psychologically corrosive. Traditional defensive doctrine taught that obstacle construction could slow enemy advances, buying time for the organization of stronger defensive positions. But if obstacles only bought hours instead of days, if the enemy could overcome any obstruction through sheer engineering efficiency, then what was the point of defensive warfare? This psychological dimension, the undermining of German confidence through consistent demonstration of American engineering superiority, was arguably as important as the tactical advantages the bridges provided. By late March of 1945, many German units were surrendering rather than conducting fighting retreats to the next defensive line because they no longer believed defensive lines mattered. If the Americans could bridge the Rhine in 2 hours, what river could stop them? The legacy of the Rhine bridges extends into contemporary military operations in ways that are not always obvious. Modern military engineering still uses modular bridge systems descended from the M2 treadway bridge. The procedures for rapid bridge construction developed in World War II remain, with technological updates, the basis for current military engineering doctrine. The emphasis on standardization, intensive training, and systematic institutional learning that characterized American engineering operations in 1945 continues to define American military culture. But perhaps the most important legacy is conceptual. The Rhine bridges demonstrated that operational tempo, the speed at which military forces can act and react, is often more decisive than tactical sophistication or technological superiority. An army that can move faster than its opponent, that can build the infrastructure more rapidly, that can sustain operations at a higher tempo, enjoys enormous advantages regardless of other factors. This insight has shaped American military planning since World War II. During the Cold War, NATO's response to Soviet numerical superiority in Europe rested partly on the assumption that NATO forces could mobilize and deploy more quickly than Soviet forces, offsetting numerical disadvantage with superior responsiveness. In the Gulf War of 1991, American forces emphasized rapid maneuver that prevented Iraqi forces from establishing coherent defensive positions. In subsequent conflicts, the American military has consistently prioritized speed and tempo as force multipliers. The Rhine bridges of March 1945 were not the beginning of this emphasis on operational tempo that has roots stretching back to earlier military theorists, but they provided a dramatic demonstration of its value. They showed that systematic organization and intensive training could enable ordinary soldiers to achieve extraordinary results. They proved that industrial methods could be applied to warfare with devastating effect. They revealed that in modern war, speed often matters more than sophistication. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.